Hi, my name is Hussain. I'm an associate research scientist at the Kuwait Institute for Scientific Research. The title of my work today is Modeling of a Municipal Solid Waste Incineration Plant for Electricity Generation in Kuwait. First, I'll start with a background on the power sector in Kuwait. The massive urbanization in the past 60 years needed continuous addition of conventional power plants to keep up with the increasing demand for electricity, 60 to 70% of which is consumed by air conditioning systems. In the past 10 to 15 years, the country needed heavy investments in the power sector to replace old steam turbines and to add to the capacity to avoid blackouts. So in Kuwait, we need a sustainable solution because we're spending billions of dinars on the power sector, and also we're burning oil, which is the main source of income for the country. Another problem or an issue of concern has aroused from the urbanization and the population increase, which is the increase in the municipal solid waste in the country, which is dumped in landfills, unsorted and without any modern environmental management strategies. So the objective of this research is to utilize the waste in Kuwait using mass burn incineration plants for electricity generation in the country. So this solution will help us solve the two aforementioned problems. And the method used in this research is through a specialized software called W2E. It's for short for waste to energy. The software calculates material and energy flow rates of the system, and the outputs are temperatures, pressures, flow rates, heat and mass flow balances of all components of the system, and subsequently it will calculate power output and the plant capacity. Table 2 shows the variation in the lower heating value, which represents the calorific value of the waste. The variation happens for scenarios 6 to 10 as we change the waste composition. And for scenarios 9 and 10, we see a significant increase in the lower heating value because the paper and plastic in these two scenarios were increased. For table 3, we see that the power output and the annual energy for scenarios 5, 9, and 10 are the highest. Scenario 5, it's because we used 100% of the waste. And for scenarios 9 and 10, although the waste is 60% quantity, 60% of the total quantity, but because of the increase of the lower heating value, it gave us a higher power output and annual energy. Two more conclusions were also drawn from this research work. The first one is that as we increase the quantity of the waste by 1 metric ton, the power output increases by 100 megajoules per 100 watts. Increases by 100 watts. Also, we discovered that a minimum value of 7 megajoules per kilogram calorific value is needed to be able to operate the incineration plant. The final table, table 4, is the economic analysis of the system or the proposed incineration power plant. The estimated values were the levelized cost of electricity, the internal rate of return, and the payback period. We can see from the table that the IRR, or the internal rate of return, and the payback period didn't change significantly due to the small changes in the installed capacity. However, looking at the LCOE, we can see that the principle of economy of scale applies for our system, because we can see that as the capacity is increased, the cost or the LCOE is lowered, and the lowest figure is for scenario 5, where we use 100% of the waste, and it's only 5.3 fills per kilowatt hour. And with that, I conclude my presentation for today. Thank you.